What's up, guys? It's Braden here. Today we're going to be talking about RC circuits. So I've written everything down and try to go through quicker, but especially on the equations later on, feel free to pause it as you're doing your own work. So what is an RC circuit? Pretty intuitive. We've got an R and a C, stands for resistor and capacitor here. There's two different types. We're going to talk about charging an RC circuit as well as discharging an RC circuit. So if we dive here straight into the details, here's an example of a simple RC circuit. We've got some sort of EMF, some sort of voltage or power source. It's going to run through a resistor. Here's a symbol in a circuit for a resistor. And then running through this capacitor here, two parallel lines will be the symbol for a capacitor. Probably refer back to your other physics knowledge, but just to be brief, a resistor is something that limits or regulates charge, and the capacitor is something that's going to hold or store that charge. So we're going to be talking about charging it or discharging it today. So if we're looking at the equations here, move this up a little bit. The charging equation is going to be your voltage is equal to your EMF, or your original voltage, times 1 minus e to the negative t divided by RC. Now, this RC can also be referred to as your time constant, or tau. That's the Greek letter for tau. You may get questions about that. Kind of not super important, and the math isn't super important, but tau is basically going to be, if you have 0 voltage and you're charging, it's going to be a little over 63% of that voltage is going to equal 1 time constant. Or if you're discharging from a certain voltage, in that 1 time constant, you will get down to a little under 37%. It takes about a little over around 5 tau to fully charge in an RC circuit. So here's a graph of charging an RC circuit. So we see that it's an exponential graph because of this e in the equation. And so you're going to get a quicker spike going up as you're charging, and then it's going to flatten out and take you a little bit longer to fully charge that. And that's just due to the fact that you're going to get a max current running through that capacitor at first, and then it's going to slow down. On the other side of discharging, you're going to have the inverse for the graph. So you're going to discharge really quickly, and then it's going to slow off as you go quicker to discharge the rest of the way. And the equation is going to be V equals V naught times e to the negative t over RC. Again, we see that RC, that time constant tau value. Kind of interesting, a little real life application for you. Some of the times we might see these equations, if you're talking about heart defibrillators, pacemakers, camera flashes, all those kind of things, those may be common in some of the problems you see. So let's run through a math problem just so we get some experience with that. So I already wrote it out. Like I said, feel free to pause it if I'm going too quick. So let's say we're charging a capacitor. We've got an EMF of 24 volts, and we're shooting for 18 volts. We want to charge it up to 18 volts. We're searching for T. So how long is that going to take if our capacitance is 60 microfarads and our resistance is 300 kilo ohms? So just to make the math a little bit simpler and make the numbers on our board a little simpler, let's do the time constant first. So R times C. So 60 times 10 to the negative 6th times 300 times 10 to the 3rd is going to be tau, and that's going to be 18. So we set it up. We've got 18 volts equals 24 volts times 1 minus e to the negative t over 18. You might see this asked in two different ways. You may see a question that says, okay, we want to know how long it takes to get 18 volts. Or you may see how long does it take to get to 75% of the original voltage. And either way is the same, because if we divide out 24 from both sides, we're going to get 0.75. So if it asks for a percent, you just set it up that way. 0.75 equals 1 minus e to the negative t over 18. Do some simple math. So minus 1, and then divide out that negative, you're going to get 0.25 equals e to the negative t divided by 18. Take the natural log of 0.25, multiply it by 18, and divide out that negative. You're going to get time equals 24.95, so just under 25 seconds. So basically what you're looking at is it's going to take about 25 seconds to charge that capacitor to 75%, or 18 volts of the EMF. If you wanted to shorten that a little bit, all you'd have to do is either reduce your capacitance, which you might not want to do in a real life situation, or try to decrease this resistance there. And that's going to give you a quicker time in order to charge it up to there. So I hope that helps, guys. Hopefully that can give you some assistance on some of your physics work and is a good review for you. Thanks.